We close our discussion of statics with properties of sections and bodies that we'll call moments of inertia. These are going to seem like very mysterious properties, and part of the reason for that is the relative absence of context, so we'll try to provide some context early. The other issue is just the phrase itself. We don't use the phrase moment of inertia in everyday language. We've talked quite a bit about moments of forces, and we know that eccentric forces tend to impart rotation to bodies. So when you see the word moment, think rotational. The word inertia is used colloquially to refer to the tendency of something to maintain its current course. In mechanics, inertia refers to a resistance offered by a body to acquiring motion. Mass is one kind of inertia, and it represents the resistance offered by a body to acquiring translation. The fact that mass is a scalar is an indication that a body offers the same resistance to acquiring linear motion, whether we push it in any one of three mutually orthogonal directions. Rotational motion, however, is not so simple. Only a perfect sphere offers the same resistance to acquiring angular motion about any of three mutually orthogonal axes. We will generally have a different resistance about every axis, and we will use the phrase mass moment of inertia about x, y, and z axes to refer to these resistances. When you see the word inertia, you should think resistance. Thus, our final set of concepts is focused on assigning quantitative values to rotational resistance. To complicate matters further, we are going to discuss two types of rotational resistance. The first of these is called an area moment of inertia, and it involves a property of a cross-sectional area. This is an important quantity in transitioning from rigid to deformable bodies. The second rotational resistance is called a mass moment of inertia, and, as stated earlier, it tells us the resistance a body offers to the acquisition of angular motion. The area moment involves a 2D calculation, while the mass moment involves a 3D calculation. It is also the case that some 3D mass moments can be expressed in terms of 2D area moments, so we'll begin with the discussion of area moments first. One way to think about an area moment is as a measure of dispersion. If we consider the two exam distributions shown on this slide, the dispersion of the exam 1 distribution is greater than that of exam 2. This is only an analogy, however, so let's take a few minutes to see how an area moment of inertia comes about in mechanics of materials. Let's consider a straight beam supported at its ends and subjected to some combination of downward loads. A beam made out of a real material will flex under these loads. We could sketch a set of cross sections on the unloaded beam, and they would all be parallel to each other. In the case of the loaded beam, each of those cross sections rotates with respect to its undeformed state, and adjacent cross sections are no longer parallel to one another. This is where our reference to rotational resistance presents itself. An area moment of inertia provides the resistance offered by adjacent cross sections to rotation with respect to one another. If we draw lines through the rotated cross sections, they eventually meet at some point. Thus, at every position x along the beam, we can define a local curvature, kappa of x, and its inverse, a radius of curvature, rho of x. If we define the local lateral deflection as v of x, and this lateral deflection is small, mechanics of materials theory, which many of you will learn about after statics, tells us that the local curvature can be written this way. The curvature, which is 1 over the radius of curvature, is well approximated by the second derivative of the lateral deflection with respect to x. And furthermore, that curvature depends on these quantities. What drives the local curvature is this right-hand side. M of x in the numerator and E and I in the denominator. The quantity m of x is our internal bending moment distribution from Chapter 8. So it represents one input to understanding how much a beam deflects under load. The quantity E in the denominator is something called a modulus. It's a material property. In terms of common construction materials, it is very high for steel, moderately large for concrete, low for wood, and very low for plastic. The quantity I in the denominator is our area moment of inertia. Think about what this expression tells us. In construction, we want lateral deflections to be so small that we're unaware of them. If you're walking across a floor in a skyscraper, you certainly don't want to feel the floor flex beneath you. If you're driving through a parking ramp, you don't want to bounce up and down like you're on a roller coaster. This expression tells us that to minimize flex, we need low loads, as measured by the internal bending moment m, stiff materials, as measured by modulus E, and a stiff cross-section, as measured by I. How does this definition of I come about? To see this, we'll consider a deformable cantilever beam and talk about what it experiences in bending. So how does I come to be defined? To do that, I'm going to use a little bit different coordinate system. In our discussions of beams, we've made the horizontal axis the x-axis, but our attention now is going to be focused on the cross-sectional area of this beam, and that's going to cause the coordinate system to be aligned a little bit differently. So what I'm going to do here is x is going to be pointing in, y is still going to be pointing up, and then our right-handed system will make this z. I'm going to suppose I have a beam that's going to have just a rectangular cross-section. And if we look at it from this end, our z-axis now is going to be coming out, and we'll have a beam that has a span, which we're going to call little b, and a height, little h. In this system, you'll notice that the xy coordinate system is going to look like this on the cross-section. And that's fine, that's what we want because our attention is going to be geared towards that cross-section. Now I've got what appears to be a built-in beam here. Let's represent that this way. And I'm going to suppose that I've got some loads that are applied to this. Maybe it's just the weight of the beam itself. And what will happen under these conditions is that the beam will deflect down this way. And more importantly, the upper fibers of this beam will stretch and the lower fibers of this beam will shrink. And so we're going to have a situation where we are both in tension and in compression at the same cross-section. The z-axis, as it turns out, is often neither stretched nor shrunk and experiences no deformation, and we call that the neutral axis. Okay, now this is a very different sort of situation than we've run into previously. We've talked about truss members experiencing either tension or compression, but we haven't talked about something experiencing tension and compression at the same location. So what does that look like? What we'll do now is take a perspective view of this cross-section. Here's our neutral axis z, and here's our coordinate directions x and y. And z is coming out. And what we end up with is a distribution of stress. So this is going to be like a pressure. We're going to represent that we have fibers that are stretched, and then as we move towards the neutral axis, the amount of stretch shrinks till it goes to 0, and then we're in compression. And what we have here is a stress, sigma z, which is linear in y. So we're going to write this as C0 times y. This is a constant we don't know yet. So I'm just going to say TBD for to be determined. The units of stress, like pressure, are force per unit area. And so what we have here, I have essentially sketched what amounts to a line load more than a stress, because as I go across the beam this way, there will be no variation in the stress. So whatever happens here at x equals 0 will extend to x plus or minus b over 2. That is, I could define a local line load here in the y direction, which would be the stress sigma z times the span b. Now, how do I determine that C0? As part of our internal force distributions, it's presumed that we've already found the normal force and the bending moment. Now, these are going to be a little bit different because they're going to be a function of z, which is along the long axis of the beam. We're going to suppose we've already found the internal forces, which for our new coordinate system are going to be a function of z, since that's the long axis of the beam. And then the bending moment will be in the x direction as a function of z. To be consistent, the resultant force and moment from our line load W of y must match our internal forces N and M. So how would we do that? We could also write our normal force as an integral from minus h over 2 to plus h over 2 W of y dy. But C0 and B are just constants, so we can pull those out, and we get an integral of y dy, which integrates to y squared over 2, and between these limits, this goes to 0. So what that tells us is that our stress distribution as we've sketched it is consistent with pure bending and no axial loads. To construct the bending moment, we take our load distribution and we multiply it by the moment arm, which in this case is y. In fact, if we look at that sketch of the stress distribution, We can think about it as a distribution, a continuous distribution of force couples that goes from y equals 0 to y equals h over 2. Here again, we'll pull the c0 out of the integral. And we're left with a y squared in the integrand, and then a b dy, which we could write as an area increment. This integral is now exactly equal to Ix. So what that tells us is that our constant in front of our stress distribution is equal to the local value of the bending moment over the area moment of inertia. And we have a stress distribution in Z, which goes like this. This illustration gave us an expression for Ix, the area moment of inertia about the x-axis. But we could define a similar moment, Iy, for resistance to bending about the y-axis, and Iz for resistance offered by adjacent cross-sections to twisting about the z-axis. It's also the case that in this particular illustration, we positioned our coordinate system at the centroid of the cross-section, but that doesn't necessarily have to be the case. Generally, the xyz coordinate system can be positioned anywhere relative to the centroid of the cross-section. Here we have definitions for 4 quantities associated with area moments: Ix, Iy, J0, which is essentially also Iz, and something called Ixy. The first 3 of these we'll call area moments of inertia. This last one will actually be a product moment of inertia. The fact that we have 3 different area moments of inertia as well as a product moment of inertia is an indication that an area moment of inertia is an unusual entity. We have previously encountered scalars and vectors, but an area moment of inertia is actually neither of these. We'll come back to the nature of moments of inertia when we discuss mass moments of inertia in section 10.3. In these expressions, the tilted quantities refer to the positions of differential element dA measured perpendicular to the axes denoted by the subscript on the area moment. Note that the orientation of the coordinate system is significant. Suppose we consider an alternative coordinate system, which we'll call x prime and y prime, and this is going to be rotated through an angle theta relative to the reference xy coordinate system. If we're considering the differential element in this figure, these now become the distances x tilde prime and y tilde prime, which are different than x tilde and y tilde in the original coordinate system. So a coordinate system rotated through an arbitrary angle theta compared to some reference system would give rise to very different values of area moments. To keep things relatively simple, we'll often position our coordinate system so that the cross-section is symmetric about one or both axes. We'll also be restricting our attention to just the area moments and not the product moment of inertia. Note that the area moments are always positive. We're integrating a positive quantity, a distance squared, over an area. Both the integrand and the differential element are always positive, so the integral is always positive. The product of inertia, which is significant for non-symmetric cross-sectional shapes, is not guaranteed to be positive. For shapes symmetric about an axis, it is 0, and for non-symmetric shapes, it can be negative as well as positive. Going forward, we'll just consider the area moments Ix, Iy, and Iz, also called J0. Note also this very important relationship between J0, or Iz, and Ix plus Iy. And this follows directly from the relationship between the R tilde in the J0 integrand and the Y tilde and X tilde in the XY in the Ix and Iy integrands. We can see that R tilde squared will be X tilde squared plus Y tilde squared, and so we can make a direct substitution into J0 of R tilde squared equals quantity X tilde squared plus Y tilde squared, and then separating those out into two different terms will give us this expression J0 equals Ix plus Iy. In some problems, the calculation of Ix and Iy will be very straightforward, and it will be easier to calculate J0 by simply adding Ix and Iy rather than starting from the integral definition. And in other cases, it will be easy to calculate J0, and we could take advantage of some other properties of cross-sections to back out Ix and Iy from J0 rather than to calculate them directly from their integral definitions. So this will be an important relationship for us as we consider the calculation of these area moments for different cross-sections. In addition to what we've noted thus far, note that the area moment has units of length to the fourth. This comes from the integrand having units of length squared and the differential area element having units of length squared. What is not obvious yet, but what we'll show in section 10.2, is that the area moments have their smallest values when the coordinate system is positioned at the centroid of the cross-section. Before doing any other calculations, we can get some insight into a basic structural element used in construction, the I-beam. What we want in construction is a structural element that minimizes its own weight and offers the greatest possible stiffness to bending, so we don't get sagging floors or parking ramps. In our previous expression for curvature, the area moment of inertia appeared in the denominator. How do we make this as large as possible? Our definitions for area moments indicate we want as much material as possible as far away from the origin of the coordinate system. An I-beam consists of two flanges spaced far apart by a connecting web. The web is narrow and close to the origin, so it contributes little to the area moment. But the flanges are far from the origin and make a dominant contribution to the area moment. The fact that the integrand consists of the perpendicular distance squared is significant. That nonlinear dependence on distance implies the area moment becomes larger at a compounded rate as we move material away from the origin. So where are area moments used? We've already discussed the stress associated with bending and the inverse relationship between stress and area moment. We have a similar expression for torsion, which mostly differs from our expression for bending by the symbols in the equation. Instead of talking about adjacent cross-sections rotating with respect to another in bending, torsion is a mode of deformation where adjacent cross-sections remain parallel but twist with respect to one another. If we were to score a straight line on an undeformed cylindrical shaft that subsequently transmitted the torque along its axis, that straight line would deform into one with a helical pitch. In the expression for torsion, the symbol tau is, like sigma, a stress. R is a radial distance from a coordinate system centered on the axis through the shaft, and J, or Iz, is the area moment of inertia of the shaft's cross-sectional area about the axis along the shaft. In both cases, we minimize deformation and stress if the area moment is maximized. The area moment also presents itself in our expression for buckling. Achieving the snap-through failure associated with buckling requires adjacent cross-sections to be vulnerable to sudden, sharp rotations with respect to one another. We can reduce the possibility of buckling by either restricting our unsupported lengths L to small distances, but we can also reduce the possibility of buckling by making structural elements from stout cross-sections that resist rotation. What are mass moments used for? As previously mentioned, mass moments of inertia provide the resistance of a body to the acquisition of angular motion. The expression shown here is a little misleading in that it appears to be a scalar equation with a single moment, a single angular acceleration alpha, and a single mass moment I sub m, but we'll remedy that in section 10.3. The point is that a definition of mass moment looks very similar to the definition of an area moment, with an integrand that scales with distance squared. It's just that now we're integrating over a mass, which in turn means we will eventually be integrating over a volume, a 3D calculation. The functional form of IM means we get large inertias, that is, large resistances to acquiring angular motion. The more material is positioned, the further away from the center of a body. This last point is best illustrated with the following example. You may already have an intuitive sense of which of these will spin more quickly if you provide a fixed moment about an axis perpendicular to the shafts. The answer is that baton A will be much harder to spin. Even though the weights are the same, the distribution of mass results in far more mass in baton A being positioned from its center. The nonlinear r-squared dependence of the integrand will compound this redistribution, making baton A significantly more difficult to spin. We define a quantity called a radius of gyration to denote a kind of average position for defining an effective area or mass moment. Again, the language of this phrase seems quite foreign, so we can rearrange the expression a bit to make it look more familiar. In this case, we could write kx squared equals the area moment with its functional form explicitly shown divided by the area. Even though the radius of gyration is not a centroid, it is a centroid-like quantity. The only difference here is that we have a power of 2 instead of a power of 1 in our definition. There is an entirely analogous definition for radius of gyration for bodies. Even though these aren't centers of mass, they are center of mass-like quantities. Radii of gyration in both cases tell us where to position, relative to an axis, all of the area and mass of distributed cross-sections in bodies so that we get the same area and mass moments as the actual distributed cross-sections in bodies. This slide provides a visual interpretation. In the case of the actual baton, the mass is distributed and the mass moment about the x-axis is defined from the integral. In the case of the contrived baton, all the mass is concentrated at radial position kx. The mass moment of the body is kx squared m and is equal to the mass moment of inertia of the actual baton. Having defined the moments of inertia, we now turn to how to evaluate them. We'll begin with calculation methods of area moments, which are easier because they are 2D. Nonetheless, we'll see that reducing these to 1D integrals is a bit tricky, as the nonlinear nature of the integrand complicates evaluation.